All right, ladies and gentlemen, good morning. Hope you guys are doing well, and welcome back to another video with Mr. Kenton for HL Chemistry. We're continuing our discussion and our notes on topic 2 on atomic structure, and we're transitioning into how atomic structure helps us understand electron configuration. And if you guys recall, a key point of information for us to understand as it pertains to electron configuration is our understanding of light. So in this particular video, we're going to be diving into the electromagnetic spectrum and also looking at the difference between a continuous spectrum versus a line spectrum. Okay, so let's go ahead and dive right in here and take a look at what we need to kind of get our bearings around. So first thing, kind of the standards, if you will, the electron configuration of an atom can be deduced from its atomic number. So that makes sense. We should be able to determine the electron configuration of an element once we know its atomic number, because we know how many electrons it has. Now, when you break that down, we start looking at how science has developed over time. We see that developments in scientific research follow improvements in apparatus. And so the use of electricity and magnetism and Thomson's cathode rays gave us greater insight into our understanding of the atom. Next thing you notice there, theories being superseded. Quantum mechanics is among the most current models of the atom. And so you think about how we looked at previously, how we had the different models of the atom, and how as newer information was made available through the advancement of technology, we were able to come up with better and better models to represent the atom. And then that last point that's listed there is the use of theories to explain natural phenomena. Specifically, we're going to be looking at line spectra being explained by the Bohr model of the atom. Okay. Now, again, when you look at these slides, this is mostly for me as a teacher to be helping you guys kind of understand what we're going to be looking at as we're going forward. Now, keeping our thought process open here, when we start thinking about how does this particular topic relate throughout the world, not just simply here in the United States, not just simply here in our HL chemistry class, but what are the implications of what we're talking about? And so the European Organization for Nuclear Research, CERN, is run by its European member states. There were 20 in 2013, with involvement from scientists from many other countries. And it operates the world's largest particle physics research center, including particle accelerators and detectors used to study the fundamental constituents of matter. And so you think about that when we talk about quantum mechanics, because we're studying atoms, we need something like this in order to better understand what's going on with the atom. And so understanding that a lot of our knowledge has not just simply come from scientists in the United States. This has been a global kind of research, a global thing that people have been working towards to better understand the atom, and specifically even electron configuration and the model of the atom. So just keep that in the back of your mind of how this information is not simply in a silo here in the United States. This is something that's been worked on across the world. Now our TOK piece, again, I like bringing you to these questions because it causes us to think about how do we know the things that we know, and what are the limitations to the things that we know. And, just here, Heisenberg's uncertainty principle states that there is a theoretical limit to the precision with which we can know the momentum and position of a particle. And so what are the implications of this for the limits of human knowledge? So just a question to consider. And then I like this quote here. One aim of the physical sciences has been to give an exact picture of the material world. One achievement has been to prove that this aim is unattainable, by Jacob Bronowski. And so what are the implications of this claim for the aspirations of natural sciences in particular and for knowledge in general? And I think that particular quote and that question kind of build into our discussion that we had on the models of the atom, that from the natural sciences perspective, it is only going to be able to explain, like science is only going to be able to explain things in the natural world. If there are things that are outside of that, then it's not going to be able to explain that particular topic or that particular idea with any degree of certainty. That's not necessarily a bad thing. It's a reminder that there is a limitation to scientific knowledge, just like there's a limitation to historical knowledge, or there's a limit to mathematical knowledge, there's a limit to literary knowledge. But the understanding is that when you use them in conjunction with each other, they can help fill in the gaps and provide you with a clearer picture of what is most likely to be true. And hopefully that makes sense. All right, so as we begin to dive into electron configuration, one of the first things that we're going to need to kind of recognize is that emission spectra are produced when photons, so tiny packets of light, are emitted from atoms as excited electrons and return to a lower energy level. Okay. And so the skills, the things that you should be able to do based on that particular content to be able to describe the relationship between color, wavelength, frequency, and energy across the electromagnetic spectrum. So let's start there with our electromagnetic spectrum. So electromagnetic radiation, we know, comes in many different forms, right? And so remember, electromagnetic radiation can be referred to as radiant energy. It can be referred to as light. So different forms of light exist. That's just a reality that we're operating under. Now, the thing that we need to recognize is that all forms of light, whether it's our highest energy light or our lowest energy light, they travel at the same speed, right? The speed of light, 3.0 times 10 to the 8th meters per second squared, or meters per second, not squared. I was thinking of an acceleration, not a velocity. But the thing that is unique about light is that they have different wavelengths and different frequencies, which account for their uniqueness. Now, when we start talking about our forms of light that have higher energy, what we tend to notice is that higher energy light has a shorter wavelength and a higher frequency. And so that's when you think about this. This is why gamma rays are such high in energy. They have short wavelengths, they have high frequencies, and so therefore they produce much greater amounts of energy in comparison to, let's say, visible light. All right, so here is the electromagnetic spectrum in order from lowest energy to highest energy. So first you've got radio waves, then you've got microwaves, then you've got infrared radiation, then you got your visible light in Roy G. Biv. That's your lowest to highest, right? Red, orange, yellow, green, blue, indigo, and violet. Those would be the order for visible light. Then you've got UV radiation, you've got X-rays, and then lastly you have gamma rays. So radio waves are going to be our lowest in energy, which means they have the longest wavelength and the smallest frequencies, whereas gamma rays, they're going to have the shortest wavelengths, highest frequencies, and the highest amount of energy. All right, so that kind of leads us through our introduction to the electromagnetic spectrum, and I know that that's something that hopefully we're familiar with. Now, another thing that we need to be able to do is to be able to distinguish between a continuous spectrum of light versus a line spectrum of light. Now, continuous, just like it sounds like, it is an uninterrupted spectrum of something. In this case, we're talking about light. So a continuous spectrum is produced when white light is passed through a prism. So if you have white light, you pass it through a prism, what you do is you get all of the colors that fall into this range of 4 times 10 to the negative 7th meters to 7 times 10 to the negative 7th meters, right? So all of those wavelengths, frequencies, and energies of light will be given off by white light. And we would call that a continuous spectrum. So it shows all of the colors in an unbroken sequence of frequencies, such as the spectrum of visible light. So that's an example of a continuous spectrum. Now, the reason why we're starting with continuous spectrum is because what we're going to see is that different atoms, when you look at their spectra, if you will, they don't have a continuous spectra. They only give off light in a very specific frequency. And so then that's when we get into this idea of line spectra. So when you take a look at line spectrum. So we're looking at the same thing. That would be the entire rectangle at the bottom, but those are very specific frequencies that are being given off by whatever it is, whatever substance it is that we're looking at. So a line spectrum is an emission spectrum that has sharp lines produced by specific frequencies of light. So notice that instead of it being the full array of colors, yes, you might have some that are in the purple and the indigo and the blue and the green and the yellow and the red. It's not all of the wavelengths and frequencies that correspond to visible light. And so that line spectrum is going to be produced when the electrons within an atom or ion move to higher and lower energy levels, right? And it's only going to correspond to very specific wavelengths and frequencies. It's not going to be found continuously over the entire spectrum. And if you think about it, if you guys remember, we have those gas tubes that you guys have looked at where you had to put on the special glasses that allowed you to see the different wavelengths of light that were being emitted by that particular gas. That's exactly what it is that we're looking at here. We're seeing this idea that the electrons exist in very specific energies, and when they've been either given or when they're moving back into a different energy level, they produce very specific frequencies and wavelengths of light that we can observe. Now, uniquely, different elements have different line spectra. So for example, this would be a unique line spectra to one specific element. And so no two elements have the same exact line spectra. And so based on that information, you can use the line spectra to help you identify unknown elements if you have the line spectra data. All right. And the last thing I want us just to kind of keep in mind is that within the IB exam booklet, like the reference sheet, they do give some data, some information, some equations and things like that that are specific to the electromagnetic spectrum, and those are found in the data booklet in section 3. All right, so I'm going to stop there for this kind of first video as we've dived into the electromagnetic spectrum and then line spectra for elements, and we'll kind of continue this discussion here shortly. Thank you guys for joining me. I hope this makes sense. If you have any questions, please feel free to stop by during office hours or during class, and I'll be more than happy to help you guys out. Take care. Thank you so much.